Okay, hello, precious one. I welcome you once again to Kenya Mathematics Classroom. On this particular episode, we are looking at the continuation of linear transformations, but this time around, we are looking at some special linear transformations. We are looking at special linear transformations, and the first type we'll be looking at is reflection. Reflection, and for the reflection, we have reflection in the x-axis. We have reflection in the x-axis. Now we are looking at some special linear transformations, and we are considering reflections. And the reflections, we have reflection in the x-axis or reflection in the line y equals 0. So we can either say reflection in the x-axis or reflection in the line y equals 0. And now this is the mapping. We have xy maps to, we have x minus y. So reflection in the x-axis can also be written as the mapping is xy maps to x minus y. So if you want to write the matrix out of it, take note, you have reflection in the x-axis. This is xy maps to, we have x minus y. That means that the x coordinate is kept the same, but the y coordinate is negated. I'll show you why we are getting this mapping. So for reflection in the x-axis or in the line y equals 0, xy maps to x minus y, we are looking at how best you can write the matrix for reflection in the x-axis. So this can be written as r of xy, and this is x minus y. Don't forget that I told you that in our previous video that the comma separate the row, the first row from the second row. So reflection in the x-axis or in the line y equals 0 of xy maps to x comma minus y. So if you are writing the matrix out of this, don't forget that our matrix will be equal to, now before the comma we have only the x term, and the coefficient of the x is 1. Don't forget that there is no y term in the expression before the comma. So that means that this should be 0. Then after the comma, we don't have any x term. That means that we have 0 here, but the coefficient of the y term is minus 1. Therefore, we are going to have minus 1. So this will be the matrix for the reflection in the x-axis. This will be the matrix for reflection in the x-axis. Now we are looking at reflection in the y-axis. Let's look at reflection. So all these are special types of linear transformation. So we have reflection in the y-axis or reflection in the line. We say line x is equals 0. Line x equals 0. And the mapping is xy. This maps to, we have minus x, we have y. So it means that for reflection in the y-axis or in the line x equals 0, the mapping is xy maps to minus xy. So the x coordinate is negated and the y coordinate is kept constant. So if you want to write the matrix, then it means you are going to have reflection in the y-axis, we have of xy, and this maps to, we have minus xy. So this can also be written as x comma y, and this is in the linear transformation form, we have minus x as the first row, then we have comma y. So if you are trying to write the matrix for reflection in the y-axis, then ry will be equal to, now before the comma we have only the x term, and the coefficient of the x term is minus 1. So we have minus 1. There is no y term before the comma, so we have 0. We are done with the first row. Now after the comma, there is no x term after the comma. That means that we have 0, and the coefficient of the y term is 1. I guess you understand what you are doing, because you have already looked at how to write a matrix when you are given the linear transformation. So in general, we have that of reflection in the x-axis or in a line y equals 0. The matrix is Rx equals 1, 0, 0, minus 1. And we have reflection in the y-axis or in the line x equals 0. And xy will map to minus xy. Now, the reason why this is giving us that is what I want to show you now. Now, let's consider this. I want to show you what is really happening so that you can understand what is happening. Now, assuming that, don't forget that we said that for the reflection, in the x-axis, xy maps to, we have x minus y. This was reflection in the x-axis. And for reflection in the y-axis, xy maps to minus xy. This is reflection in the y-axis. Now, let's take note of this. I want to explain something so that you understand why the mapping was like that. Why the mapping is like that. Now, let's consider the xy axis. We have y here. This is the negative y-axis. We have the positive x-axis and we have the negative x-axis. Now, assuming that we have a point, say the point is A, that is 2, 3. Now, point A, 2, 3. With the point given, that is A, 2, 3. The x-coordinate is 2 and the y-coordinate is 3. So, on the x-axis, let's assume that we have 2 here, and on the y-axis, we have 3 here. So, that means that we are going to have our point A here. Now, when we are reflecting this point, that is point A. Don't forget that the point A is 2, 3. So, if you are reflecting this point in the x-axis, then that means that we are assuming that this is our mirror. This is our mirror. Now, if you have the point in front of the mirror, take note that the distance from where the point is to the surface of the mirror will be the same as the distance from where the mirror is to where the image is found. Don't forget that the point on the x-axis here is 2. So the point will still be the same. But the distance from where the point is to the surface of the mirror will be the same distance in terms of magnitude from the surface of the mirror to where the image is. But don't forget that if from here to here is 3, then from the origin to the image is also 3. But on the y-axis we have minus 3 because we are in the negative y-axis. So you realize that this point A, that is 2, 3, is now giving you another point, and the point you are getting, don't forget that the x-coordinate is still 2, but the y-coordinate now is minus 3. And so when we say that with the reflection in the x-axis, xy maps to x minus y, that is the x is kept constant, but the y is negated. This is what we are talking about. We are assuming that the x-axis is the mirror line, that is the mirror. And so we are reflecting this in the x-axis. Now, assuming that you are reflecting the point A, 2, 3, in the y-axis, reflection of the point 2, 3 in the y-axis, that means that this will rather now be our mirror line. That is the y-axis. So if you have the point 2, 3 and you're reflecting this in the y-axis, then it means that if this is the surface of the mirror, then the image will bring you somewhere here. And this will be another point. So let's assume that we have A2. Let it one be A1. Now with the A2, don't forget that the x-coordinate will still be 2. That's the distance from where the initial point is to the surface of the mirror will be the same as from the surface of the mirror to where the image is. Don't forget that we are now reflecting in the y-axis. So this is what we are. This is now taken to be the mirror. So if from here to here is 2, on the x-axis it will be minus 2 because we are in the negative x-axis. But the 3 will still be the same. So we have the x will change to be minus 2, but the 3 as the y-coordinate will still be the same because we are still on the negative or on the positive y-axis. So when we are reflecting in the y-axis, you can see that it is the negative, the x-coordinate that is negated. That is why reflection in the y-axis, xy maps to minus xy. So you see that the x has been negated and the y is kept constant. But with the reflection in the x-axis, the x is kept constant, but the y is negated. So that is how come we have that mapping. And I guess by now you know that when you are giving reflection in the x-axis, you can write the matrix, and when you're also giving reflection in the y-axis, you can also write the matrix. So in general, that is really what is happening. So with the reflection in the x-axis, as you are now seeing, if you want to write the matrix, then don't forget that we say that x, y maps to x minus y. So if you want to write the linear transformation in this form, then it will be x, comma, minus y. And if you want to write the matrix, simple, it will be now before the comma, we have only x term. So the coefficient of the x term here is 1. There is no y term, so 0. After the comma, there is no x term, so 0. But the coefficient of the y term is minus 1. So this will be the matrix for reflection in the x-axis. Now, for reflection in the y-axis, take note. With the reflection in the y-axis, the coefficient of the x term is -1, but there is no y term, so you have 0. Then when you check the second row, there is no x term, so this should be 0, but the coefficient of the y term is 1, so this should be the matrix. So in general, that is how we bring out the matrices when you are given the linear transformation and you are looking at some special transformations. What we are looking at is the reflection in the x-axis and reflection in the y-axis. That is what we have looked at so far. Now we are going to continue with our special transformations. We are now looking at we have reflection in the line y equals x, and for reflection in the line y equals x, the mapping is xy maps to yx. So you see that xy maps to yx. That means that we interchange the positions of the x and the y. So if you have xy, this maps to yx. The y will be up there and the x will be down here. So the positions of the x and the y coordinates are interchanged. So that is reflection in the line y equals x. And if you want to write the matrix for reflection in the line y equals x, this will be xy, and this will map to, we have the first row, so y, comma, then the second row, we have x. So if you want to write the matrix for reflection in the line y equals x, this should be equal. Now before the comma, there is no x term, so we are going to get 0 here. The coefficient of the y term is 1. After the comma, we have x term. The coefficient of the x here is 1, but there is no y term, so it is 0. So reflection in the line y equals x, the matrix is 0, 1, 1, 0. 0, 1, 1, 0. Now let's look at reflection in the line. Now we are looking at y equals -x, and the mapping is xy also maps to, we have -y minus x. So the x and the y coordinates are also interchanged, but this time round what is really happening is, we negate the y and we negate the x. And so if you want to write down the matrix for y equals -x, this can be expressed as -y, comma, then we have -x. If you want to write it in this form, this is how it is written. Take note that the comma separates the first row from the second row. So if you want to write down the matrix for y equals -x, this will be equal. Take note, before the comma there is no x term, so we have 0. But the y term, the coefficient is -1. After the comma, the x term coefficient is -1. There is no y term, so 0. So this will be the matrix for reflection in the line y equals -x equals 0, -1, -1, 0. So if you know how to generate them, there is no need trying to memorize them. When you can write the mapping, you can generate the matrix. So that is reflection in the line y equals -x. Now we are also going to look at enlargement by the scale factor k about the origin. We also have what we call the enlargement by a scale factor. Enlargement by a scale factor, say k. And enlargement by the scale factor k can also be written as, we have enlargement by the scale factor k. So we have xy, and this maps to, it will be k times the xy, and this can be expressed as, this is the scale are now multiplying, so we have kx, k times y, then we have ky. So in general, this, if you want to write down the matrix for the enlargement by the scale factor k, then this can also be expressed as xy. This maps to the first row, we have kx, comma, then we have ky. And don't forget, how do you write the matrix? You now understand. Now before the comma, there is an x term, and the coefficient of the x term is k, so we have k. But there is no y term, and so we have 0. Now when you look at the expression after the comma, that's the second row, there is no x term, so we have 0 for that, but the coefficient of the y term is k, so we have k. So in general, if you are given enlargement by a scale factor k, this is the matrix, and where the k is a constant, it can be a number. Now when we start solving problems, you understand these things we are talking about, and these are special linear transformations. Now, we also consider we have the anti-clockwise rotation of theta degrees about the origin. So we are also considering the anti-clockwise rotation about the origin, and that one is also given by, we have r of theta, where the theta is the angle. Now this expression is given by, we have x cos theta, we have plus y x cos theta, then we have minus y sin theta, then we have x sin theta, then we have y cos theta. So if you want to write down the matrix, then the r of theta will now be equal to, we have cos theta here, then we have minus sin theta there, then we have sin theta here, then we have cos theta here. This will be the matrix. So let's assume that we are given anti-clockwise rotation of 90 degrees about the origin. Then the matrix for the rotation and the clockwise rotation will now be cos 90 degrees, then minus sin 90 degrees, then we have sin 90 degrees, and we have cos 90 degrees. And don't forget that cos 90 is 0. Sin 90 is 1. Because of the 1, we are going to have minus 1. Then sin 90 is 1, but cos 90 is 0. So this will be the matrix for anti-clockwise rotation of theta degrees about the origin. So r of 90 degrees will now be equal to 0 minus 1, 1, 0. So these are the special linear transformations we are going to consider. Now we'll be solving a lot of problems, and we are going to involve all these so you understand it better. But on this particular episode, that will be all for now. Thank you.